Da-da-da, if the bridge collapses, that's okay because I've got a hoverboat. Okay, we're looking at a linear expansion of a bridge. This is an example problem. Nothing's here, so let me describe what's going on here. We have a bridge with an original length of 200 meters. So it's about 600 feet for those of us who are more familiar with American units, or imperial units, I should say. And this bridge has a length of 200 meters at the temperature of 20 degrees Celsius. It's very important that we know that initial temperature. Otherwise, what's the delta T going to be here? What we would like to know is, what is the change in length for the bridge whenever the temperature goes down to negative 30 degrees Celsius, which it absolutely can during a polar vortex, or if it gets as hot as plus 40 degrees Celsius. What we do know is that our bridge has an alpha value of 12 times 10 to the minus 6 inverse Celsius. So that Celsius is in the denominator and the units work out. And like we said in a prior video, those alpha values are very small. Large ones are like minus 3. Oftentimes they're minus 6. You can get a minus 9. Like, they're small values. Okay? So, let's take a look at this. Let's first do this when it's hot outside. When it's hot outside, we'll use the red color. The new length of if we want to just find out like what the delta L is of that bridge, we know the delta L is equal to just L naught alpha delta T. In our case here, this isn't difficult to solve at all. We know that's 200. We know this is 12 times 10 to the minus 6th. What we need is the delta T. Delta is always a final minus initial. Our final temperature was 40. Our initial temperature the bridge was created at was 20 degrees Celsius. If we multiply all this together using El Calculadora, we'll get a number, which, numbers, but it is what it is. So 200 times 12 times 10 to the minus 6 is 0.0024 times 20 gives us 0.048 meters, or 4.8 centimeters. So like about 2 inches. That's not a lot. But let's look at things when they get cold. Same equation, L naught alpha delta T. And when we run this, we're going to get 200 multiplied by the 12 times 10 to the minus 6th. The final temperature here when it's cold is negative 30 minus the initial of 20, which gives us a full value here together of negative 50. When we run this, we get 200 times 12 times 10 to the minus 6 times negative 50. We get negative, or a shrinking, of 0.12 meters, or about 12 centimeters. Which means all in all, between a super, super cold winter month all the way up to a very, very hot summer month, our bridge, when we combine these together, it could shift by approximately 0.168 meters. And the reason why I have 0.168 is because when I'm thinking about the differences here, I'm thinking of this as an absolute value when I add them together. Because this is how much it could shrink by, that's how much it could grow by. The total difference between all of them is 0.186. You can either do that by calling both values negative and getting a full negative value, or making them both positive and working from there. But 16, 17 centimeters, that's quite a bit of distance. An inch is 2.54 centimeters, so we're talking here something like 7 to 8 inches of gap, of space on the bridge. So your bridge might expand and contract that much. That's the space for a foot, as I see it. And then the bridge eats you. But that's for another day. If you're more interested in looking at things like linear expansions, you might also be interested in the stresses that come with this. If you are interested, with the stresses that occur on materials as they're expanding or contracting, then you might want to look into civil engineering. But there is something known as a Young's modulus that comes into place here, where if we wanted to look at something like concrete and get a little bit more technical, we could say that a delta L was equal to 1 over E, where this right here is known as Young's modulus. Modulus. Spelling is not my game. And then we start thinking about pressures here, or rather, forces divided by areas and the original length of our object. We're not going to talk about that within the AP Physics 2 curriculum, but if you are interested, start looking up some of the Young's modulus, because if you're going into civil engineering, you will need to start thinking about the actual forces acting over areas of things like your roads or buildings that you're designing, and the physical properties of the substances you're building them out of as well. Because, let's face it, I like my bridges to stay up when I'm driving on them. But, until next time, stay safe on those bridges. Adios, and take it easy.